Okay, we're going to do lesson 3.2, exponential and logistic modeling. We're just going to build on what we did in 3.1. First thing, we got to remember how to convert some stuff, percent, decimal, etc. Remember, 16%, move the decimal point, 0.16, 0.05 is 5%. Show how to increase 25 by 8% using a single multiplication. I want to increase by 8%, so instead of just adding on, multiplying on 25 times 0.08, we can actually do 25 times 1.08. We want to end up with 108% of what we started with. 25 times 1.08 gives us 27. Solve the equation algebraically. Divide both sides by 20. B squared is 36. Take the square root. B is plus or minus 6. Principal square root would be plus 6, but keep in mind that it could be minus. This guy over here, divide by 123. I get 0.64. I get B cubed equals 0.064. At this point, you can take the cube root, or I think it's easier just to raise both sides to the 1/3. Take the answer that's in your calculator, raise it to the 1/3. B is 0.4. So hopefully you remember those little tidbits from previous courses. Population growth, basically what we're talking about here. If a population P is changing at a constant rate, so 3.1 was all about y equals a times b to the x, where a was the initial value and b was that base. Repeated multiplication. So if you compare that to this, P of t equals P naught, not peanut, 1 plus r to the t. You'll notice this is the initial population right here. The base is going to be 1 plus r, where r is going to be our rate of change. So that's where it kind of comes back to 8% would be 1.08. X and the t are very similar. So it's really exactly the same equation as y equals a times b to the x. Tell whether or not the population model is growth or decay. The only thing that we're looking at here is going to be this guy. If 1 plus r is equal to 1.021, this is going to be a growth of 2.1%, because it's our 1 plus 0.021. That's where it comes from. There's our growth. Determine the exponential function with an initial value of 10. There's our initial value, and we have the rate of 8.1. So we'll have P of t is equal to initial value times 1 plus 0.081 to the t. That's awkward, so add it up. P of t equals 10 times 1.081 to the t. There's a function. Nothing wrong with y equals initial value times, we knew it was growth, so do the same thing. Nothing different with the y equals a times b to the x compared to the population function. Suppose a culture of bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will meet 350,000. So what we've got here is we've got our starting point. We've got our time and population. So time and population at said time. And if we make a nice little XY chart here, like good little 7th graders, we have at time 0, we have 200. Oh, there's our initial value. And it's doubling every hour, so after time 1, we go to 400. Time 2, we went to 800. Time 3, I could be here all day. I'd go to 1600. And we can see that our initial value is going to be this guy. And then we are doubling each hour, so it's going to be growth. And doubling, if we go back to what we did yesterday, times 2 times 2 times 2 is there, but we are actually increasing in terms of a percentage. What is our growth rate? We are actually growing at 100%. So it's almost easier to start this one as y equals 200 times 2 to the x. Well, what's the 2 over here? The population at time t is equal to the initial population times 1 plus r. Well, that's 1 plus 100%. Doubling means you added yourself to it. So that's where r is 1. We don't see an r as 1 very often. Usually when we're talking about populations, we're talking about small percentages. So there's our equation. If we want to predict when this is going to be 350,000, then again, much like in the 3-1 homework or lesson, I can do this. In a couple of days, we'll be able to do this with logarithms. But right now, you could either fire this into your y equals and look at the table, see when it hits 350,000, or graph this in y1, graph this in y2, and calculate the intersection. The only thing you got to do is you got to watch out for your window. You want to make sure you set your window for your x's for time. So that's going to be number of hours, and then set your y's for your population. So you got to get up to at least probably 400,000. And you should be able to see when they intersect and see what you're going to get. I think I got an answer around here somewhere. Looks like 10.77 if you found when that 350,000 is equal to, right here, when are they equal to each other? 10.77. It's going to be hours. Maximum sustainable population, we talked about that for a logistic function. If we're talking about 1,500 students in a high school, 5 students heard a rumor, started a rumor, bad kids. If you remember yesterday, this up top is our maximum sustainable population is 1,500. That's going to be the number on top. So they start the rumor at the end of day 1, time equals 0 is the day that the rumor spread. So at the end of day 0, if you go S of 0 is equal to 1,500 divided by 1 plus 29 e to the negative 0.9 times 0. Well, if you think about it, that's 1,500 over any e to the negative 9 times 0, that's e to the 0, that's 1. This is 1 plus 29. This whole thing is just 30. So at the end of day 0, 1,500 divided by 30, we have 50 kids who have heard, 50 students heard it by the end of day 0. And then we could continue on. Now, you can type this into your calculator, into y equals, put that in there. And if I want to know when we're going to reach 1,000 students, when will 1,000 students have heard the rumor, you can look at the table, scroll down, your x's are your days, your y's are your number of students, or set it equal, put y1, this is y1, put this as y2, and calculate their intersection, and you'll be able to see how many days until that happened. Looks like it's 4.5 days. If you put that into the calculator, you can see what's happening. That's it for 3.2. Hope you enjoyed your time.